Okay, so with that, thanks for having me. I am Karttikeya, and I am a fifth year PhD at UC Berkeley, soon to graduate. Today, I'm excited to present some of our work that's very hot off the press called EgoSchema, where I will introduce to you a diagnostic benchmark for very long form video language understanding. And this work is done jointly with Rayambek Akshalako and Professor Jitendra Malik at the Berkeley AI Research Lab in UC Berkeley. So, as you guys know, we have made a lot of progress dealing with images in the last 5 to 10 years. If you think about computer vision in the three broad pillars, there's the pillar of recognition, where we talk about things like object detection, instance segmentation, human pose detection. This is sort of where computer vision was making the biggest strides 4 or 5 years ago in 2014 and then in 2016 with Mascar CNN. The next pillar is of reconstruction, which is where we want to reconstruct the 3D world as it appears to a human. And in this, we talk about technical problems like novel view synthesis, 3D scene reconstruction, amodal 3D pose detection. And this has been, of course, a hot area for decades, but recently got a resurgence with the introduction of implicit techniques like NERF from the last 2, 3 years. And then finally, we have got the area of reorganization, also popularly called generation, where we try to make new images or new 3D scenes or new 3D videos, uh, sampling from the data distribution. And here we have problems of scene decomposition, image manipulation, and synthesis. And this, of course, is what is getting the most attention now in form of generative AI in computer vision with diffusion models leading the charge. So this is all great. And, it seems like, images are very much technology that is commercially viable. But if you look at the world, it's not, something that happens in images. It really is a dynamic world, and it happens in videos and movies and long movie clips. Well, these things simply just don't get captured in the modern computer vision systems for the most part. And if you look at the state of video understanding, you would realize that that is actually far behind. So if you look at the same three pillars in videos, recognition, reconstruction, and generation, the results look impressive, but there is a one, key aspect that is missing from all of these results. If you look at them carefully, I believe it should be very visible. Does anybody in the chat maybe want to take a guess on why, what's the missing ingredients in all of these results? Yes, that's right. So this is all operating in the level of seconds, right? If you look at these videos that I'm showing, they're all in a few seconds. And with a few seconds, you move on to the next video and then do the same thing again. And that's cool and all for, let's say, if you want to make recommender systems for TikTok or, see if Instagram Reels are toxic or not. But it doesn't really capture how humans understand the world. Humans really understand the world in long temporal contexts. When we go and watch a movie, let's say Lord of the Rings, or recently I watched Oppenheimer, we have context of what has been happening over long periods of time. We can do perception and reasoning over agents' goals, behaviors, and intents in a rich, dynamic, contextual setup. And the same is true not just in movies, but also over lifetimes, which is measured in months, years, and beyond. And so the question really arises is that clearly there are temporal scales of dynamic perception. At the very shortest scale, we have snapshots, which are images. The next scale is of short clips, such as the ones in YouTube Shorts or Instagram Reels or TikTok videos. But then there is a very long range of temporal understanding that simply doesn't get explored in modern computer vision and is in fact very underdeveloped, as a lot of which will a lot of our quantitative results will show that later in this talk. So what can we do to start making progress along these very relevant to our everyday intelligence areas? And also, this has to be an endeavor that not only considers videos in isolation, but is truly rich and multimodal, right? We want to be able to integrate other forms of sensory information like audio and also language while we are scaling up our video pipeline to deal with seconds and hours of data. So of course, like I was saying before, most of the video data sets are too short. Here is a snapshot from a video data set that is popularly used today in research. It's called AVA, Atomic Visual Actions. And if you notice, even though the video itself might seem like it's a few seconds long, the labels are all very instantaneous. So in case of AVA, the labels are labeled every second. So it's a 1 Hz frequency. And even in other data sets, they are usually labeled every few seconds. So they do not really capture long-term video understanding. I don't need to look at a minute of video to realize that this person is sitting or that person is talking or third person is bending. It really is, clearly graspable to a human from a couple seconds. And in fact, just having a long video doesn't actually mean that it's a long-term understanding tasks. For example, consider this video of Michael Phelps racing in 2015. The original video is 1 minute 39 seconds. But if you, for example, consider these questions, you might think that they do not require watching the whole video. And how much of the video you need to understand really depends on the question that you're asking. So in terms of, suppose the first question, which is what water activity is being shown, which really is the task of action classification. To answer swimming, a human doesn't really need to look beyond even a couple frames, right? Any frame of this video would really tell you that swimming is what is being shown. And that really is the level at which most of the current video methods operate. Now, if you consider the second question, which is what swimming stroke are the swimmers doing, then of course it requires watching it a little bit longer because you kind of have to observe exactly what it is. But again, I think in a matter of a couple of seconds, not a couple of frames, so still an order of magnitude higher. But in a matter of a couple of seconds, you would still be able to say that, hey, this is butterfly stroke. And then finally, in the third question is, how did Michael Phelps change position in the race over time? Now, this is a question that requires watching the video much more intently, because not only have to you identify Michael Phelps, you have to track his position over time, you have to track everybody else's position over time, and then you have to find the relative difference between their positions to really understand how he is doing over time. And more importantly, this also doesn't seem like something that you can answer from just looking at a few frames of the video. Now, all of these questions are really about the same video, but the task that they implicitly determine is really different based on the question. And that's really the point I was trying to make when I say that long video doesn't necessarily mean long-term temporal understanding task. So then how can we actually understand how long of a task a given task is? Because clearly video length is not a good solution. So to that end, we introduce a new conceptual tool that we call temporal certificates, which really is a simple idea. The idea roughly translates to what's the smallest part of a video? What's the smallest set of subclips that are both necessary and sufficient on their own without referring to other parts of the video to convince a human verifier that the annotation that is marked for that video is in fact the correct annotation. So that is to convince a human verifier of the veracity of the marked annotation. So said in other words, suppose I'm go back to this example of Michael Phelps and water activity. So in terms of temporal certificates, I would ask the question, what's the minimum part of this video that if I show a human, they would be able to say that they're swimming? And clearly that would be maybe a few frames at any point suitably chosen in the video. So then the temporal certificates for that particular question will roughly be 4 or 5 frames and so on. So this is a conceptual notion. It's not really possible to find this from a machine learning method. It really requires having a human in the loop to be able to find the certificate, but it helps us understand how difficult of a temporal task is. And you could do it noticeably not just for any particular task, but a broad variety of video language tasks. In fact, it doesn't even need to be language. You could still do action classification, which is traditionally thought of as a pure video task because the classes are labels, not really natural language. And it would still very much be applicable, the notion. So this notion is, cuts across a variety of data sets and benchmarks. It doesn't really matter which particular task you're looking at, and it would give you a notion of how hard or difficult that task is. So we do that. We take this notion and then we employ, this notion on 15 different video data sets and benchmarks. And across these 15 data sets and benchmarks, we find out how difficult every one of these benchmarks is. So if you look at, for example, on the plot that I'm showing on the screen, on the x-axis, I have the video clip length, which really is just the average length of the video in that data set. And on the y-axis, I have the certificate length, which is the length of the temporal certificates that we had marked for that data set. And we simply plot them on a 2D grid. Now, data set that would be as long as the, whose certificates are as long as the videos that the data set is comprised of would lie on the y equals x line, and anything below that line really has much smaller temporal certificates. So if you notice, actually most of the data sets, every data set except 4, really falls in this tiny small rectangle near the 0, 0 of this plot. And this really comprises of most popular data sets that people in videos use, like Kinetics, UCF, something, MSR VTT, AVA, YouTube M, IVQA, How to QA, HVU concept, and more. And for all of these data sets, really, even if the video clip length gets longer, so for example, How to QA has a video clip length of about 17 seconds, the certificate length is still quite small. Most of the data sets actually have certificate lengths less than 2 seconds. So if you recall, the certificates are the minimum part of the video that a human has to watch to be able to be convinced of the veracity of the answer. And so really 2 seconds is enough to convince a human of the veracity for all of these data sets. Now, if you go beyond that, the biggest data set that we have is long-term video understanding data set. The data set is itself called long-term video understanding data sets, that is abbreviated as LVU. And I apologize for this slide mishap. I think there's some sort of automatic timer that triggers every now and then. So if you look at the LVU dataset, even though that the video clip length is more than 3 minutes, on average it's 200 seconds plus, the certificate length is still less than 20 seconds. So most of the data sets simply are, something that can be solved in 2 seconds. Even the longest is 20 seconds. So of course, Voxel 51 had a super nice sticker that I had seen in CVPR that now I'm remembering. It just calls something to the effect of data eats model for lunch, right? If I'm not misremembering, Jimmy can correct me if I am, but data eats model for lunch. So if you have data sets that are less than 20 seconds, your models are not going to be long-term video understanding models either, right? It will still be very short. So in that case, this kind of drives my point that to make progress on having data sets that models that can understand hours of video, we need to make such data set. And I'm excited to say that I believe we have done so for the first time in our work that I'm presenting. So here's a short teaser video. I will not say something for the first 10 seconds, and then I'll chime in. So EgoSchema is a new data set with about 250 hours of video, where the task is different between each data set. So if you look at these 4 videos, every question really requires understanding the full video. And we have verified that with humans based on temporal certificates. So if you look at the concepts, the questions, for example, in this question, the question is analyze the key concepts C takes to accomplish the task and discuss their significance in the context of the overall video narrative. C is really the camera wearer. This is something that is clear this way throughout the entire dataset. And the videos themselves are also from the perspective of the camera viewer. So these are what I call egocentric videos. Now, if you look at the questions, they really are something that you can't answer from just a couple seconds. So if you want to see, for example, this question, identify the primary tasks or tools used by C in the video and what was their intended use, you can notice that even without looking at the video, this would require careful watch of large parts of the video because you really need to understand what is primary and how much C is using every one of that. So for example, let's try it out ourselves. This is one of the questions from the data set. Yeah, questions are free form and they don't really depend uh, on anything besides the video. So if you look at, for example, this question, what inference can be made about C's handedness while play the piano? I would like you to watch the video as it plays. It's sped up, of course, and then try to guess the answer. So the first option is C mainly uses both hands while playing. Second is C routinely alternates between the hands while playing. Third is C frequently switches between hands and using right hands for gesturing. Fourth being the hands together dominate the performance, but right hand occasionally takes over for added emphasis. And five is C mostly uses right hand, with small portions played with both hands. Right. So I believe if you try to make a guess now, I would like to see if you get it right. When I tried it the first time, I did not get it right because I got bored at some point and didn't really pay attention to what's happening in the video. And that's precisely the point that we are trying to make with this data set, that you really need to understand all of it. You can't get your way around it. And even and I think something happened at towards the end, but even state of the art models struggle a lot with a task like this because they can't really skip around in the video and they need to understand all of it. 3 minutes is quite a bit of video content for models that are usually trained to look at a few seconds. So humans on this achieve an average score of 76%, while state-of-the-art models have less than 35 seconds. And EgoSchema has average certificate length of 100 seconds, which is what I was talking about earlier. So here's another video in which I'm going to highlight as the video plays what part of the video is the certificate. So in this case, you can see that every time there's a certificate, there's a certificate icon on the top. And so you can see that most of the video actually is the certificate for this particular question, which is identify the most crucial items C interacted and explain their relative importance. And the parts of the video that are not certificate are grayed out. So these are the parts that you can skip while showing to a human, and they would still be able to guarantee that the correct answer is indeed correct. And there it is. That's a brief overview of EgoSchema. So now that we understand what EgoSchema is, I will dive into a bit more detail on what's happening. So let's say, let's look at the plot again, but this time with EgoSchema in the plot. So you notice that EgoSchema video clip length are about 180 seconds, which is 3 minutes of video, while the certificate length are about 100 seconds. So the average certificate length is 5.7x longer than certificate length from nearest video datasets, which is very good compared to something like LVU, which is only at 20 seconds, and is in fact 1 to 2 order of magnitude bigger than almost all other video understanding datasets. So we believe this is quite an important direction in pushing researchers to truly understand the difficulty of long-term video. Now, so far, I haven't really talked about how the dataset was collected. And you might think that this dataset might be collected in sort of the same manner as other datasets, which is that, hey, you write some guidelines for a human and then you try to get them to follow those guidelines and collect the dataset as they go on annotating. but it is not so. And in fact, and perhaps I should highlight this earlier, if you look at these questions, they're all free form. These questions really sort of capture the video in a way that if we try to get a human to do, it will take a lot of time. It requires not just recognition, but actually creativity to come up with different questions for different videos and make sure those questions have long certificates and can be answered by the video and do not have confounders and all that. And so for that reason, we actually employ a very nice mix of rule-based filtering, large language models, and human curation. So now I will walk you through the data generation pipeline. If you look at the data generation pipeline, the first thing is we start from the raw data, and then we choose to filter this data based on some rules about how long of a data we want and how much of a narration density we want. So all of the videos come with manual narrations that humans have done per second to sort of explain what is happening in the video. These narrations don't really capture any questions. They are just visual descriptions of the actions being performed. So we start from the raw data. Then next we do question answer generation, and this is done using LLMs that look at the raw data, look at the narrations, and try to generate a question that will involve watching a large part of the video. They also generate the correct answer for that question, and they generate 4 other wrong answers per clip for a total of 5 options. Now, once we have a large amount of question answers generated per video, we take that and we do keyword filtering and generate question answer validation to make sure that the generated topics and the generated answers actually can be found out from the video. And then, of course, we do LLM-based QA filtering, where we set up several baselines, such as let's try to guess the answer to this question without looking at GPT-4 and without looking at the video with GPT-4, because GPT-4 does not support videos yet. And if GPT-4 can guess the answer to the question without looking at the video, it means that is not a very good question. And so we should not have such questions in the dataset. Or let's say we try to generate the question again, and this time we get a different correct answer. So if for the same question and for the same video, we get a different correct answer every time we try to generate it, that probably means that any one of those correct answers are not very good. And other unit tests like this to do some logic validation of these generated questions. And these really cut down on the number of hallucinations that we get from the large language model step in this pipeline. And then finally, the fourth step is manual QA curation. And in this case, we simply give these videos to the crowdsourced workers and ask them to find out any remaining videos that have wrong labels, are misformed, the correct answers are not correct, or in most of the cases, more than one of the wrong answers are correct. So in all of those cases, we ask the QA worker to discard that video. And this really makes this process much more efficient, because discarding a video is a much less time consuming step than looking at the video and thinking of a question, thinking of an answer, writing the wrong answers, making sure the wrong answers are wrong, and so on. So by offloading a lot of this annotation work of generation to the LLM, while using humans to do curation or discrimination only, makes this whole pipeline way more cost efficient. And that can enable actually collecting data of this type at scale, which was something that was simply not possible before for computer vision, long-term computer vision tasks. So finally, after this whole process, we are able to generate 5,000 high quality question answer pairs that cover 250 hours of video. Now, once we are done, we were very excited to go and try it out on state-of-the-art models, where somewhat expectedly, somewhat unexpectedly, we find that almost nothing works. So even state-of-the-art, largest 7 billion plus parameter models achieve less than 33% accuracy on multiple choice question answering on EgoSchema. in a setting where random choice is already 20%. So here are some of these models. I won't belabor the details too much, but they really are the best models out there for video and language tasks. And pretty much nothing can get beyond 32.1%. And if you compare that with humans, you see a big gap. Humans, for example, can get up until 76.2%. And even if you constrain them to only be able to answer the entire thing in 1 minute, so not just look at the video, but look at the video, look at the question, and answer the question in less than 1 minute, they can still achieve 67%, which is still double the accuracy that the best models can achieve on this data set. Not to mention that if you don't constrain them, or if you constrain them in the proper format, there is a 76.2% a number that humans can achieve on EgoSchema. And to me, this highlights a huge gap that exists between current model performance in long-term video understanding and human performance, and also presents an exciting opportunity for future research in this direction. And as I like to say, with EgoSchema, long-term video is now open for business. So I think that's mostly the top level technical details I would like to highlight. Thank you for listening to the talk. All of the stuff I talked about is open source. So all the paper data models are all out there to use. Here's the website that you could go to. If you want to find it out online, I believe if you just search EgoSchema on Google, all of these details would come up. So you don't really have to go through this. You can just go through Google with EgoSchema. The data repository is also online, and I also welcome you to star it if you think it's interesting and would be something useful to you, or even would like to keep an eye out. The paper is open sourced and available on archive as well. And that's it. Thanks so much. I will now take the questions.
Yeah, Karthik, looks like we have 3 questions in the Q&A widget.
Okay, let's try it. Okay, so the first question from Faye is, I'm new to AI. Could you explain the difference between reconstruction and generation? Okay, so I think this really is talking about the first part of my slide deck. So let me go back and reshare. So Faye, the difference between reconstruction and generation really is about the organization of the data. So if you look at reconstruction, it really isn't converting or generating any new pixels. It just is a transformation of how the 3D world would look from a different angle. So there is no question of hallucination in a reconstruction model, for example. If it would have that data or it would have that information, it would show that information. If it doesn't, then it wouldn't. It's simply so for the easiest way to think about reconstruction, it's like moving the camera around in a fixed scene, while generation really produces new information. It tries to make up a new scene based on the user's preferences, and so of course it can hallucinate in the process, and that really is the fundamental difference. Okay. The second question was, can we detect face gestures? I'm not very sure, Adrish, what you mean by that. Do you mean in the videos, can we see what the people are doing from their faces? If so, I would have to say almost no. There's about 5 to 10% of the videos in EgoSchema that don't have blurred faces. And that's by the consent of the people in the video. For the rest, people who have not consented with, we have blurred their faces. So you wouldn't be able to detect face gestures for the most part. And the third is from Faye, why the piano answer, not 4? Okay, so I think that's referring to the video again. So let me go. Okay, here. So, I mean, this sounds like something that will require a lot of time because it's a long-term video. But both answers to there dominate the performance with, okay. And well, I think the main reason is because the part of like the total time that he's playing with both hands versus the time that he's playing with just one hand is roughly similar. So he isn't actually dominating the performance by using both hands. He's using both. He's using one hand as well, roughly the same amount of time. But we could. I mean, it's a detail, so I might be missing something more. But I think that's roughly the answer. Okay, thanks, Faye, for the question. So Nathan Thomas asks, could EgoSchema generation process be suitable for real estate video data? Absolutely. There is really nothing that, I mean, the diversity of the data in EgoSchema is truly astounding. I wish I showed more of the videos that are in there, but really we have, I mean, I think actually we might even have one thing from construction, not really real estate, but construction. Let's see if I can find that example right here. So in this video, I think I did show you something that was related to construction. So right here, right in the top right video is actually a person, I think, putting together some construction materials in a building. And this and lots of other building slash construction videos are part of the data set. I'm not super sure of what exactly you mean or what kind of real estate, but yeah, it could be applied to that as well. In fact, it works just as well. Because large language models, which is really the main source of the questions, are extremely generalizable. Cool. Thanks, Nathan. Okay, I think that's all of the questions.
Yep, that looks like it.
Actually, Nathan has one more. Do we have time? Because I know we have just hit 30-minute mark.
Yep, just go for it.
Okay. So Nathan also asks, can EgoSchema answer the question, what is the curb appeal of the property? Uh-huh. So, well, EgoSchema is a data set, Nathan. It really isn't a model. So EgoSchema won't be doing much answering. Models trained on EgoSchema might be able to answer something like that. Yes. But this is really just a data set. So if you want to answer that question, you would have to include that question as part of the training data and then train some models for that part. This isn't, yeah.
As a side note, it may be interesting to review. I think maybe 2 months ago, we had the folks from Open Door do a presentation about how they're using computer vision to answer questions like, what is the curb appeal of this property? What is the price that it should be listed at, et cetera. So I'll include that in the follow-up post as in regards to that particular talk from the Open Door folks, who I think are trying to solve this exact problem. Oh, one last question there from Jen. Karthik, if you have time.
Of course, very cool, Jimmy. Thanks for chiming in. So Jen asks, can I ask random why it's called why it's called EgoSchema? Great question. So it really is called EgoSchema by taking inspiration from a very old data sets in NLP, which is called Vinograd schema. I'm not sure if you're familiar with that data set, but it is sort of a small collection of, I think, 200 or so questions, which in modern day and standards is pretty much a blip on the large data oceans. But it really stood out as a hard nut to crack for several years. And it was not until the 100 million billion parameter models that really killed that data set. Before that, most of the language models couldn't actually make progress on Vinograd schema. So the schema part really borrows from that previous generation of data sets. And ego, because again, as I was showing it to Nathan earlier, most of our data sets are shot from the ego perspective. So if you look at these videos, which I always seem to not be able to find, okay, like these guys, all of these videos are shot from the perspective of the user. So that's why it's ego, because it's egocentric view, which is the view of the camera mirror, instead of being a third person view, which is the view you would see in CCTV cameras and the like. So that's the name EgoSchema.